Good evening, everybody, and welcome to the end of our sun, or at least I should say, welcome to a lecture entitled The End of Our Sun. This is in fact lecture 2 in my series on cosmic conclusions, but it's also the first of a 2-lecture series on how stars evolve, what their life cycles are. And there are 2 lectures because the way that stars evolve and the way that they play out and the way that they come to an end depends very, very strongly on how massive a star is. The subject of tonight's lecture is going to apply to the lower mass end of stars, stars much like our sun. And the subject of my next lecture is going to be how massive stars end, much more massive than our sun. And it turns out they end in rather different ways. There are some similarities, both are fairly spectacular, but there are some key differences. So as we think about the life cycle of stars, I just want to draw your attention to how it all begins and to show you this particularly exciting image, which was recently published by NASA, a beautiful result from the new JWST, its newest space telescope. We refer to it as the Just Wonderful Space Telescope. What you can see here is a very famous nebula in the night sky known as the Pillars of Creation. I'm sure you've seen this before. It was an important target imaged by the Hubble Space Telescope, the JWST's predecessor, at optical wavelengths a few years ago. And while there are a number of similarities with this image, there are a number of important differences that I'd like to draw your attention to. So this particular image is taken at longer wavelengths than the original optical image from Hubble. Specifically, the waveband that we're talking about is the mid-infrared, significantly longer wavelengths than in the optical. And the importance of observing at these longer wavelengths in the mid-infrared is that it reminds us that there's a lot of dust in the universe, clouds of dust, which when they're cool enough can collapse under gravity and form new stars. Stars themselves are much fainter at these longer wavelengths, these mid-infrared wavelengths, and also dust is much easier to see at these longer wavelengths. So this is the image of choice if you want, or this is the waveband of choice, if you want to image a situation where stars are going to be born in the future. One thing that's really important about this image at the mid-infrared range is that there has never been such a sharp image at these wavelengths. Until the JWST came along, we had never looked at the universe in such sharp focus at these long wavelengths. Let me draw a comparison for you with slightly shorter wavelengths, not as short as the optical, but now the near-infrared. So this is exactly the same region of sky, but at a different wavelength. We're seeing a different picture because at these somewhat shorter wavelengths, the stars are a whole lot brighter, so they come booming through, and also we don't see the dust quite so readily at these wavelengths. And that's because of the temperature, the relatively cool temperature that the dust is at. This image too is from the JWST, that magnificent telescope that was launched on Christmas morning and delayed many of us from getting to our roast turkey. The launch of this telescope, the deployment of this telescope, the images extracted from this telescope are a testament to the dedication and the expertise of a great many scientists and engineers working in the US, working in Europe, and way beyond. I want to introduce one of them in particular to you, and that's Gillian Wright. She's based in Edinburgh. She was the European principal investigator for the camera that works at those mid-infrared wavelengths that I mentioned to you in my second slide. She's also the director of the UK Astronomy Technology Centre. And the fact that this camera on the JWST works so brilliantly is a brilliant testament to her and to her teams. So here then are these two images, and you can see how very many stars there are at the near-infrared wavelengths, and how much there is in the way of dusty clouds at the mid-infrared wavelengths. So beautiful images. We could spend the whole hour looking at these and talking about these, but we need to get to the business of the life cycle of stars like our sun, and we need to think about how stars form. Now, wherever you have gas in the cosmos, if it's cool enough, it will gradually begin to form stars. As long as that gas cloud can collapse under gravity, ultimately, you will end up with stars. Stars will form wherever you have the condensation of primordial gas, that's gas milling around, formed after the Big Bang, or indeed interstellar gas, the spewed out remnants of X stars. More of that a little bit later. But if you have gravitational collapse, we call it Jeans collapse, under gravity of gas, ultimately, following a competition between gravitational collapse and thermal energy, which is fighting to oppose the gravitational collapse, ultimately, you will end up with these dense concentrations of gas, mixed in with dust, no doubt, which will, once they're cool enough, properly collapse. But as that gas gets denser and denser, it will get hotter and hotter. And when that happens, once you attain sufficiently high temperatures, fusion can be ignited. And I just want to play for you this cartoon movie which captures rather more eloquently than I can that process. So this is a great big cloud of gas, or it's a simulation of a great big cloud of gas in the galaxy. There's a bit of residual rotational motion which manifests itself as spinning faster and faster as it gets closer to the center. You'll notice that this gas has collapsed into a disk, and that disk is perpendicular to the direction that the gentle rotation or the spin of the gas is taking place on. As the collapse persists and progresses further and further, you'll get a star right in the center, at the central potential well of this gas cloud, and you'll get little condensations formed at different radii further out. Those initially are protoplanets, and where they're surrounded by disks, those are the progenitors of rings of material that orbit around planets and subsequently can form satellites, much like the moons of Jupiter or the moons of Saturn. So that's pretty much how the life of a star begins and how the life of planets around our star begin to take place and form the solar system. Now, with a bit of flagrant disregard for getting everything to scale here, but just for the sake of getting everything on one slide, this lines up all the planets that we know and love. This is how the planets look, approximately, after the elapse of 4 or 4.5 billion years after that initial condensation out of the cooling gas cloud. So we're there, the third planet out, and booming away on the left is our sun. The sun itself, right now, shines brightly, or at least our friends and relations on the other side of the world will hopefully be assuring us it shines brightly. It's night time here in London, of course. So from our vantage point on Earth, or somewhere on Earth, what we see now is a distant but blindingly bright, and I do of course mean blindingly bright light in the sky. That's what we see for now. We orbit around it, and at some point, somewhere on the planet, someone will be seeing that blindingly bright light in the sky that is our sun. The sun is our faithful companion. In living memory, the sun has been there. It's risen in the east, it's set in the west. How is this going to change, and how on earth will this play out? How will it end? How will the sun go away? Is it changing now? Well, one thing I'd like to just make quite clear is that the end of the sun is not like a sunset. The sun doesn't just glide below the horizon of Earth as it does at the end of the day on a particular location on Earth. Sunsets are a rather beautiful spectator sport to when we have time and indeed clear enough skies and clear enough horizons to watch them. But that's nothing to do with how our sun will end its life as a star. On the contrary, far from just fading into oblivion, the sun will go through some rather spectacular processes, almost as though it has read that amazing Dylan Thomas poem, Rage, Rage Against the Dying of the Light. I learnt this poem at school, loved it, and have never forgotten it. Do not go gentle into that good night. Old age, I feel sure Dylan Thomas was thinking of main sequence stars rather than humans at this point. Old age should burn and rage at close of day. Rage, rage against the dying of the light. That, in poetic form, is pretty much what our sun does as it approaches the end of its life. So right now, the sun is shining brightly, but it is not, as a star, unchanging. We can study its activity from satellites that can fly close to the sun, and we can also study how the sun changes when there's something in the way to block out the light. And that ideal something is Earth's own satellite, the Moon. By an extraordinary coincidence, our Moon is the exact same size as the sun. The fancy way of saying that is that the Moon subtends the exact same solid angle, as viewed from Earth, as the sun does. And what that means is that when you line the two up, such that the Moon is in between the Earth and the sun, if it's the other way around, you've got an apocalypse. We're talking about an eclipse, when you've got the Earth, then the Moon, then the sun. When they're exactly lined up and you block out the solar disk, then and only then is it safe to look at the sun with the unaided human eye. And when you do have the eclipsed sun, and when you do look at the residual brightness around the outside of the eclipsed sun, then you see two rather important features, which are just about discernible on this image. One is the corona, that's the white glow, more of that later, but I want to talk first about these prominences. If you look at that pink thing at about 1 o'clock, that's what is known as a prominence. A prominence is the spewing out or the spitting out of a filament of hot plasma by the lively sun. Think of it as being erupted out or belched out and spat out by even hotter and indeed magnetized sun. These prominences are absolutely huge relative to the Earth. Let's just try and see how huge that is. So here is the Earth, and now let's scale it down to the size of that prominence. So that's pretty much how small we are. You can actually fit 109 Earth diameters across the diameter of our sun. So our sun has over 1 million times the volume of Earth. Earth is really pretty puny, but it is a great vantage point with which to study these prominences. It's an okay vantage point for now, but as I'll describe later in my lecture, as the sun evolves, it gets bigger and more luminous. When that happens, it would be extraordinarily dangerous to look at the sun, even when the moon comes in front of the solar disk, because the kind of annular eclipse that you'll get would be disastrous for human eyes. More of that later on. But in terms of these prominences, that tells you that the sun is a very lively place, spitting out plasma, belching out mass at very high temperatures, highly electrically charged. Now, I took this particular photograph of the eclipsed sun in 2017 in the United States, in Idaho, along with some very dear friends. And this particular image I took on my camera. The exposure time was about 1/500th of a second. And I took it in the hopes of trying to see some of these pink prominences. But during totality, I also experimented with taking some longer exposure time images to try and go deeper on the corona and try and pick that up. Because the corona of the sun also tells us about the activity of the sun. So changing the exposure time on my camera to 1/2 a second brought forth this image. So that dark disk is still due to the moon. The moon, of course, never radiates its own light. It only ever reflects the sun if the sun is at a favourable angle. But of course, when the sun is eclipsed, no light on this side of it. And what you see in that 1/2 second exposure is a considerably extended solar corona, the extremes of which are more than a solar diameter away from the edge of the disk of the moon there. You can see it's not at all circularly symmetric. It's distinctly elongated to about 1 o'clock and 7 o'clock. So I was terribly pleased to see the solar corona. By the way, I should mention the sun isn't the only star in this image. One of the many exciting things, and there are many exciting things about an eclipse, is that stars that are normally up in the daytime, if they're nearby the sun, you can actually, when it's eclipsed, you can see those clearly. So that's Regulus, which you never normally see in August, which was the time of year when these photographs were taken. So seeing a big corona and seeing quite a distorted corona is a sign of a very lively sun. It's a sign of magnetized plasma streaming away from the sun, energized by all the convective processes going on within it. So if you see a good big-sized corona, you know that the sun is fighting fit and blasting away. Now, it was especially encouraging to see this because at the time of this eclipse in 2017, we were heading for what's known as solar minimum. That's a time in the rhythm of the sun's activity. It's got a 22-year cycle when it's at its least active and least explosive. So it was pretty good to see a couple of prominences during this particular eclipse, as well as to see quite an extended solar corona. Now, the most recent solar minimum was during 2019, and I was lucky enough to be able to get to another total eclipse then. This one was in Chile, not in the US. And this was a handheld exposure during totality where you can see a very extended corona. Let's just zoom into that right now. Again, pretty much a sun's diameter's worth to the top right and to the bottom left. So even during that solar minimum time, a very active sun. Now, the other evidence that you get of a lively and active sun is sunspots. These are much fewer in number during this so-called solar minimum in the 22-year cycle, whereas during solar maximum, obviously, you see a lot more in the way of sunspots. Even in that 2017 eclipse, we could see some little sunspots just appear. We were able to focus in on them just before totality, and even though it was relatively close to solar minimum, they were still there. If you'd like to compare the characteristic presence of sunspots close to solar minimum, as these guys are, with sunspots close to maximum, then I can show you a photograph imaged by my friend and colleague Steve Lee, very close to solar maximum in 2003. And you can see blemishes all over the sun. The solar disk during this one, a lot more in the way of activity. So there is this cyclic pattern with the sun every 22 years, and we can zoom in on those and admire them greatly. I talked a little bit about the magnetic nature of sunspots in my lecture last year entitled Magnetic Universe. So let me now show you something of the cyclic nature of our changing sun. It's got a rhythm in the sun every 22 years, as far back as records began in the 1750s. So these peaks that you see are periodic with a period that's around 22 years apart. We're just beginning the 25th cycle of the sun since records began. We're about a third of the way through that, or not quite a third of the way through that. But cycle 25 is where we're at. You can see that superimposed on that 22-year cycle, there are some peaks that are really quite high, such as cycle number 19, which was in the 60s. Goodness knows what was going on then. In contrast with cycle number 5 in the early 1800s, when the sun was much more muted. The proxy, or the metric for activity here, is something referred to as sunspot number, which is a way of accounting for the number of sunspots that you've got all over the solar disk and the number of groups of sunspots that you've got over the solar disk. It captures the real-time activity of the sun. So if you compare cycle 5 with cycle 19, you can see there's a certain amount of variability. It's been suggested that there are other periodicities besides this very pronounced 22-year cycle that are superimposed on top of this and giving you beats, but really we need a few more such cycles to be sure about that. It's also worth commenting that superimposed on that periodic behaviour is a lot of stochastic, more random behaviour. And so if I now just zoom in on the end of this plot, just showing the last couple of cycles, and now swapping the proxy for activity with the kind of radio flux, the intensity of radiation that we get at radio wavelengths from the sun, over cycle 24, just at the beginning of cycle 25, you can see that there's a lot of stochastic activity superimposed on that. So for a start, you can see even though the model of the sun's behaviour, given by this rather smooth red sine wave, is a very clean prediction, reality is not like that. In particular, for cycle 24, it came through a minimum just after 2010, and then rose up, and it was as though we had two peaks in the solar activity then, before it decayed back to its normal minimum levels around the time of the 2017 total solar eclipse and the 2019 total solar eclipse. Since the early 2020s, the solar activity has risen again, ahead of what the prediction of the model says. So the black line there is the observation, and the blue line is the sort of smoothed approximation to that black data. And as you can see, the sun is much more active than the model is predicting. So the sun is not following anybody's rules. in detail. It's following the basic rhythm that we've seen in the past few centuries. But right now, the sun is very active. One beautiful consequence, by the way, of the sun's activity is when some of the ejected mass from the surface of the sun, the so-called coronal mass ejections, actually end up all the way around Earth's magnetosphere and then propel in towards the poles of our planet, the magnetic poles, and give rise to the beautiful northern lights in the northern hemisphere and southern lights in the southern hemisphere. These so-called aurorae are absolutely spectacular, and with the sun being so active at present, it's a terrific time to go up to Scotland, and on the assumption that you get a non-cloudy night in Scotland, there are high chances that you'll see some really beautiful aurorae. Some spectacular examples have already been seen this year. But there are times, in contrast with now, when the sun has been really quite inactive. So let's now turn our attention to that. So there was something referred to as the Maunder minimum, which was a period of extreme inactivity by our sun. This was pretty much it began around 1645 and it ended around 1715. So that's a span of about 5 Gresham professors of astronomy. UK prime ministers hadn't been invented back then. That didn't happen until 1721 with Sir Robert Walpole. And of course, I wouldn't dream of suggesting that the increase in hot air after that event was in any way linked. That would be quite inappropriate. Well, before detailed records of the activity of the sun hadn't begun at the time of the Maunder minimum, in the sense of the quantitative records, counting numbers of sunspots and all that kind of thing, is the case these days and has been the case for the last 24 and a bit, 22-year cycles. But the fact there were no proper quantitative measurements available doesn't mean that we have zero evidence of the sun's activity during that time. There's a particular heroine in our story at this point, thanks to the German artist and observer Maria Clara Imart. During an eclipse that took place within the Maunder minimum, she made a beautiful and accurate, we believe, sketch of what the solar corona looked like at totality during an eclipse in, I think it was 1706. So that's her drawing, and it's available in a library in Germany even today. Now, before we get sniffy about the fact that this is the representation by an artist, not by NASA or some satellite, let me draw your attention to some important details. The solar corona, as depicted in this image, is this blue concentric annulus centered on the dark grey eclipsed sun. The dark grey, of course, being the surface of the moon that's facing closest to us here on Earth. It's circularly symmetric. No hint of those elongated streaks in the solar corona. Now, before you dismiss this as some inaccurate representation of someone using artistic license, it turns out, and there's a paper by Hayakawa et al., that if you look at the representations by other artists of this exact same eclipse, then they all show the corona around, when you scale the eclipsed solar disk to be the same size as Maria Clara's, then you find that the corona has pretty much the same size as well. So I think for this particular eclipse, which took place in 1706, which was in the middle of the Maunder minimum, the idea that there was no expansive asymmetric corona, I think, holds water. In another eclipse that took place during the Maunder minimum, John Wybard, who was able to view the 1652 eclipse in Carrickfergus in Northern Ireland, said the following: "The ring around the sun had a uniform breadth of half a digit." I think that's old-fashioned language for a finger. Half a digit, or a third of a digit at least, that it emitted a bright and radiating light, and that it appeared concentric with the sun and moon when the two bodies were in conjunction, i.e. when they were in eclipse. So very small, circularly symmetric corona goes together with inactive sun, which is what was the case, we think, during the Maunder minimum. Well, the sun is much, much livelier these days, and indeed, it's a very important source of energy for those of us who live and eat here on planet Earth. So the luminosity of our sun, that is to say the power radiated by our sun, is absolutely tremendous. It's something like 10 to the power 30 watts, 10 to the power 30 joules every second. Now, planet Earth is sufficiently close to the sun that we can receive, on average, for every square metre of Earth, an average of 1,000 watts for each of those square metres from it. So that's quite a lot. And if we can collect it and harvest it, it is enough, more than enough, to sustain life on the planet, allowing plants to grow and be eaten by animals who eat other animals. The sun is the engine behind all of that good stuff. And the sun's energy, accumulated over millennia, metamorphoses into chemical energy, which is stored under the ground in coal and oil and gas that we burn in a flash in our internal combustion engines. There are other ways that we can do this. But nonetheless, my main point is our nearest star is the source of all our energy for living, eating, and having our being. So what does the sun do? Well, I find it amazing to think that it's the source of our energy as well as the source of gravitational attraction that means that we orbit around it. And I find a real resonance with what Galileo said some years ago. The sun, with all those planets revolving around it and dependent on it, can still ripen a bunch of grapes as if it had nothing else in the universe to do. I'd like to update this very slightly by saying the sun, with all those planets revolving around it and dependent on it, can still charge your photovoltaic panels and your batteries as if it had nothing else in the universe to do. The sun as the source of energy is particularly close to my heart because one of my observatories, my observatory located at a school in rural southern India, could not function were it not for directly collected solar energy collected in photovoltaic panels, 12 square meters of solar panels, shown here with some Indian schoolgirls for scale. My observatory simply couldn't function without that as the source of energy. And it's super important for communicating to these impressionable teenagers that once you've got the infrastructure in place of panels, a few regulators, and some batteries, thereafter for free, you get energy enduringly out of the sky. As it happens, on Friday, I'm going to be heading to my school observatory in South Africa to start building the exact same thing, because the power situation in South Africa is a nightmare, not just for astronomy at night, but for daily life. In that part of the world, they're undergoing all sorts of power outages. And when you get a power outage 4, 5, 6 times a day, then all kinds of things stuff up. Freezers don't freeze, traffic lights don't stop the traffic, or they do, but it all gets snarled up. It doesn't regulate traffic. The internet goes down, communications go fut, business and growth comes to a halt. And so solar energy has an important role to play in both astronomy and daily life. So hooray for energy from the sun. But where does that energy come from? What's the origin of all that energy? Well, it's nuclear fusion. It's the fusing together of nuclei where you have atoms or ions, ionized atoms, with sufficient energy that they can overcome the strong repulsive electrostatic forces that would normally keep them apart and enable them to fuse together to become heavier nuclei. This happens in the center of stars like our sun, where the temperature exceeds 10 million degrees. And it really doesn't matter whether the degree scale here is Celsius or Kelvin when you're talking about that many degrees. But when you are at those sorts of temperatures, a proton and a proton can fuse together with other with neutrons and other particles, and ultimately form deuterium, heavy hydrogen, and then helium, and other so-called light elements that are reasonably high up in the periodic table, like beryllium, from which we ultimately get helium, as I'll show you in a second. The exact same fusion processes with different pathways can give us the heavier elements as well, such as carbon and nitrogen and oxygen. But nucleosynthesis within stars, within our own sun, is what's going on here. It's been happening since surely after the beginning of time. It happens throughout the universe. Wherever you have a star shining, it is shining because of fusion within. This is definitely the case in our nearest star at present. And despite the gloomy nature of the title of my talk, it will continue to go on in the center, in the core of our nearest star for another probably 5 billion years. So let me reassure you about that. Some naive calculations said that surely the sun would only last for about 1 million years. Well, with a proper understanding of both nuclear physics and quantum mechanics, then the evidence is that the sun would last much, much longer. And I would say that we've got at least 5 billion years before we use up all our nuclear fuel. And I'm thinking in the first instance of hydrogen. A hydrogen nucleus is just a simple proton, and that fuses together to form heavy hydrogen, deuterium, and beryllium, as I said, in a pathway that ultimately leads us to helium. Helium can fuse with helium. And what's particularly significant about the element helium is that it was, despite being the second most abundant element in the universe, it wasn't discovered on our planet at all. It was discovered in the sun. It's relatively rare on Earth because if it's in gaseous form, it's whizzing around at the typical temperatures in our atmosphere so fast that it exceeds the escape velocity of atoms of Earth, and so it flies off utterly unbound by Earth. So we never tend to see too much of it in Earth's atmosphere, although there are cases where it's trapped underground just as well for us. Helium arises on Earth as the result of radioactive decay from much heavier elements such as uranium. But it was, as I say, discovered on our nearest star, the Sun. It was discovered during a solar eclipse. This one was the eclipse where it was discovered was the 1868 one, where Pierre Janssen discovered that there were lines in the solar corona of the eclipsed Sun that couldn't readily be accounted for in terms of all the elements that were known in the optical spectrum of elements that were already known on Earth. It was independently discovered by the British astronomer Norman Lockyer later in the same year, but also in the Sun. Initially, there was a suggestion it was a new element, but that was ridiculed. But of course, that was the right answer. Helium had never been seen before on Earth, so of course it was startling and extraordinary to suggest that there should be a new element. But a few years later, when Palmieri was examining light from lava from the volcano Mount Vesuvius, the exact same spectral line was seeing corresponding to helium here on Earth. The element helium is named after the name for the sun, the Greek name for the sun, Helios. So that's where that name comes from. And if you'd like to see an image of the solar corona during the eclipse when helium was first discovered, this is it. Forget any concentric ring of a very inactive sun here, but the corona was splurging out. And so it was relatively easy to examine the light from this corona during that eclipse. So we've said that fusion gives us stars when we've had the collapse of those gas clouds that I talked about at the start of my talk into sufficiently dense coagulates that the temperature would become high enough to give you fusion. Fusion is what gives us sunshine. Fusion in normal stars, like our sun, is when you can transform hydrogen into helium and, importantly, heat and light. You will get, in the course of the sun's lifetime and in the lifetimes of other much more massive stars, other heavier elements. But that's the subject of my next lecture. But for this lecture, I just want to introduce you to the ideas that at different radii within the ball of hot plasma that is our sun, you have different zones. And it's the very central zone, the central core, where fusion of hydrogen into helium via a pathway I'll discuss in just a moment takes place. That's happening now. That's going to persist for a few more billion years. It's way further outside that we get sunspots and prominences and indeed the solar corona itself. Let me tell you a little bit about the fusion pathway that takes place right in that central core of the sun. Each pair of hydrogen nuclei, the central nuclei of hydrogen atoms, also known as protons, fuse together, releasing a neutrino and a neutron to give us heavy hydrogen. These can then form with another proton, a normal hydrogen nucleus, releasing a gamma ray, forming what's called 3 helium, 2 protons and 1 neutron. So a charge of +2, but a mass of 3. When 2 of those lightweight helium nuclei get together, they're not that stable, but when they get together, hydrogen protons are again released, but we form stable 4 helium, 2 protons and 2 neutrons. But the heat and the light, the gamma ray, the gamma there symbolizes a ray of light, a photon. That heat and light is the side product of the fusion process, which gives us this much heavier nuclei. So that process is ongoing and will continue for the next few billion years, roughly maintaining the temperatures, and according to all the other physical processes that are going on in the sun, the conservation of angular momentum, the laws which govern the dynamo processes of the magnetized plasma that I discussed a little bit in my lecture on the magnetized universe, those are all ongoing for the time being. The heat and light that's given off is, of course, what we receive at Earth, and this will totally continue until we run out of the fuel that's on the left. When all the hydrogen is used up, big changes are going to happen. But what govern the fusion processes for the time being is, again, that usual competition between gravity, that is mass, the attraction due to mass, pulling everything in on the one hand, and gas pressure and radiation pressure tending to oppose that. Gravity squashes in, and gas pressure and radiation pressure tend to hold up the star against gravitational collapse. The temperatures inside the stars are describable and characterizable in terms of the T is the temperature and V is the speed at which these nuclei whiz around within the hot plasma within the sun. The mass is just the mass of whichever particle you're talking about, and Kb is just a constant of thermodynamics known as the Boltzmann constant. But roughly speaking, that's the relationship between the temperature that the sun is at and how rapidly stuff is whizzing around within it. The temperature of the sun will change if there isn't any more hydrogen to fuse together into helium. It'll start to collapse down. But when it starts to collapse down, the density will increase and the pressure will increase. And so things will start to whiz up again and the temperature will increase again. And so this whole cycle, while being a bit modified on small timescales for the next few billion years, will undergo dramatic change at the point all the hydrogen is gone. And this is a very significant milestone in the life cycle of the sun, when the sun begins to turn into something known as a red giant star. What happens is that that innermost core, which used to contain hydrogen, doesn't contain hydrogen anymore. It only contains helium. It scrunches down, it's collapsed down, and so that increases the temperature. The surrounding shell of that helium core now heats up, and now fusion can take place further out in the star, because that gravitational potential energy that's released when the helium collapses heats up its surroundings, and now you get hydrogen fusion taking place outside of the core of our sun. You no longer get fusion taking place in the core of the sun. That's all helium for the time being, but you do get fusion taking place in the hydrogen that's outside of the helium core. So this is the beginnings of the star turning into a red giant. Now that we've got a shell burning meaning fusing, outside the helium core, the extra heat from that collapsed helium core will enhance the fusion of hydrogen in that outer shell. Because that process increases, a lot more energy is given off, and the star will expand and get bigger. It'll actually get a little bit cooler in the process as it puffs up, but the radius will increase by something like a factor of 100. When this happens to our sun, it is goodbye to Mercury and it is goodbye to Venus. Now, our sun is by no means the first red giant in the history of the universe. On the contrary, there are some very well-known stars nearby that you can see in the winter sky when you haven't got clouds in the way that you might like to look at. If you find Orion, which is probably the best known constellation in the northern sky, and you go up from his belt through the top of his bow, you end up at a bright star called Aldebaran. It's en route to the Pleiades, which I've discussed previously. But Aldebaran is a very famous red giant star. So too is Betelgeuse in the top shoulder there of Orion. There are a great many red giant stars in the sky. Many of the named stars, or quite a number of them, are red giants because they're big and they're very, very luminous. Because the stars are very expanded, the opacity is lower, so more photons get out more quickly than in the sun when it's in its current evolutionary stage. Aldebaran its name is derived or believed to derive from the Arabic Aldabaran, which means the follower, because it follows the Pleiades through the sky. It's the 14th brightest star in the sky, and its radius is 44 times that of our sun. But it's got about the same mass. but it's vastly more luminous than the sun. It's something like 450 times the luminosity of our sun. It's also redder. So that's why it's called a red giant. It's a giant because it's bigger, and it's red because the spectrum is more red. I've shown you this spectral view of the Orion constellation in my lecture on unravelling rainbows the year before last. And if you look at Betelgeuse, the red giant, or red supergiant even, and you resolve the light from it into its spectrum, you can see that there's a big chunk of red emission if you disperse its light into a rainbow. If you compare that with the rather blue star at the opposite end of the Orion constellation, then you see, relatively speaking, more cyan-purple light and a bit less red light. There's not zero red light in a blue star any more than there's zero blue light in a red star. But what the relative redness or blueness of a star's appearance does communicate is the different temperature within. So in fact, out of the stars in Orion, Rigel is way hotter than Betelgeuse and than our sun. It's got a temperature of about 1200 degrees. Now you can approximate the temperature of the fusing ball of gas that is a star by a thermodynamic function called a black body function, which has this sort of shape of intensity of light that it radiates against frequency of light increasing this way, or equivalently wavelength of light going that way. So Rigel, being much hotter, has a much flatter spectrum in the visible part of the spectrum that our eyes are sensitive to. Red is on the left here, and blue is on the right. So the flat spectrum means that Rigel, relatively speaking, has a bit more blue light, whereas Betelgeuse has a distinct slope. It's got distinctly less blue light relative to its red light because it's at a lower temperature, because it's so expanded, a temperature of only about 3,600 degrees. So that's why the colour of a star that we see with our human eyes is a very direct indicator of its underlying temperature. And its temperature is a strong indicator of its size. But it's not quite that simple. In fact, the governing parameter of a star's evolution and luminosity and behaviour and all that sort of thing is its mass. And that's going to be the subject of my next lecture. But for now, when you see different colours, that's telling you about different temperatures of a star. So the way that stellar evolution unfolds is primarily governed by its mass, but in turn, it's governed by how much nuclear fuel you've got left at the centre. When you've used up all the hydrogen in your core, you will collapse whatever's left, in this case the end products of hydrogen fusion, into a helium core. You will then heat up an outer hydrogen shell. That will fuse. That will heat up its surroundings. You'll have a red giant. When you've used up all the hydrogen, so fusion is no longer happening, there's another big hiccup, there's another bit of a collapse, and then when all the helium scrunches together, you can sometimes have a helium flash, and to some extent the exact same process repeated, but with helium being the star of the show, where you get a helium and a helium fusing together to give carbon and nitrogen and oxygen. It's plausible that this could play out in the case of our sun. How long does it take for a star to become a red giant? Well, it's definitely a few hundred millions of years, and that won't take place, as I say, until another 5 or so billion years from now. But like I say, how stars evolve depends on their mass. When low-mass stars, and by low-mass stars I mean stars with the mass comparable with our sun, about 1 solar mass, when they've used up all their hydrogen fuel, it will expand to give you a big red giant. All stars, like our sun, will do the same thing. the radius will expand and engulf Mercury and Venus. I should say that the jury is out on whether the Sun will expand as far as Earth's orbit around the Sun. That isn't clear. It's widely agreed that Mercury and Venus will certainly be engulfed. It seems to be widely agreed that Mars will not be engulfed. We're in the danger zone. We are likely to get buffeted and blowtorched by prominences and wind from the expanded red giant characteristic of our Sun. So, you are here for now. Earth's orbit won't change too much, probably. I say probably because the mass of the Sun isn't going to change a whole lot, and that's what governs the orbit of the Earth around the Sun according to Kepler's laws, which are built on Isaac Newton's laws. But there will be some subtle effects caused by the very expanded and distributed nature of the Sun's mass. There'll be tidal effects that start to cause the Earth to probably spiral in a little bit. There won't be life on Earth at that point. The smart money is on getting over to Neptune, I would suggest. But let's ignore that suggestion for the time being. What happens to a red giant? Well, as I've said, when low-mass stars use up all their fuel and expand into a red giant, when they use up all their fuel, collapse inevitably follows. You might get a new burst of life when helium is the star of the fusion show, but ultimately, collapse under gravity when all those fusion fuels are spent and used up will inevitably follow. And you'll be left with something that is a white dwarf, a type of compact object that's very well known in the universe. I've previously illustrated in a past lecture or tried to illustrate the density of white dwarf material by illustrating that a tablespoon of white dwarf material weighs the same as a family of elephants. But I want to give you a new way of thinking about the density of a white dwarf, the relic of a star, today. So a white dwarf is a compact object having the mass of our Sun, but the volume of the Earth. That's how dense a white dwarf is. A white dwarf undergoes no fusion. It's compact. It is simply supported by electron degeneracy pressure. If it were any greater, it would form a different kind of compact object, either a neutron star or a black hole, which are the end points of much more massive stars when they approach the ends of their lives. But that is what I'll be talking about in my next lecture. As a white dwarf forms, it blows off a shell of gas, all that gas that's on the outermost periphery of the solar surface as the core collapses inwards. But that shell of gas can be very beautiful. And it's at this moment, as the white dwarf, that compact object forms in the very center, that something else beautiful is born. And that something else is known as a planetary nebula. A planetary nebula is not at all a planet, but it was so named, we believe, by William Herschel because it was a bit extended and it was not star-like, it was planet-like. But of course, as telescope technology improved, it's possible to image them as shown here in the case of the really beautiful Helix Nebula, probably the closest planetary nebula to Earth. If you image it just in oxygen light, you can see a very strong central concentration. If you image it in hydrogen light, this is with some of my Global JetWatch observatory instrumentation. If you image it in hydrogen light, you see much more of a shell structure being blown off. And if you image it in nitrogen, it looks different, very different to oxygen, a little bit more similar to the hydrogen. Hydrogen is rather more pervasive in the center, and there's a bit less nitrogen in the middle as well. You can combine these into a multicolour image, And that's when you see this beautiful structure that's shown here. I'm showing it with a different transfer function just to show the richness of the beauty of a planetary nebula that gets formed around the outside, spat out and thrown off and gradually expanding, ejected from the collapse of that central white dwarf. Really beautiful shock structures can be seen. So I'd like to end this lecture with the thought that the end of our sun is not imminent, but it will be spectacular and it will be beautiful. Thank you.
Thank you, Professor Blundell, for a very beautiful lecture, as you said. Unfortunately, we won't have time for questions this evening, but please join me in thanking Professor Blundell for another fascinating lecture.